Alright, welcome back to gases. In part 2 of these videos, we're going to be looking at gas laws, specifically Boyle's law, Charles' law, Gay-Lussac's law, the combined law, and Avogadro's law. Get out your calculators, let's go. Let's start with Boyle's law from Sir Robert Boyle. He was an Irish-English chemist that lived in the 1600s. He was describing the relationship of pressure to volume, and what he said was when pressure increases, volume will decrease if the temperature is constant and the temperature is held the same. So remember, 1 atmosphere is the same as 760 millimeters mercury, which is the same as 760 torr. We're going to need that conversion later, just hold on to it. But Boyle's law essentially says when I put more pressure on a gas, I'm pressing down on the gas. And when I'm pressing down on the gas, the volume will go smaller. Twice the pressure, half the volume. So if we were looking at a graph of pressure versus volume, since they're inversely proportional, notice that the slope is negative instead of positive. And let's see, 4 liters gives me 3 atmospheres of pressure. If I double the pressure to, 0.3 atmospheres. If I double the pressure to 0.6 atmospheres, then I've got 2 liters instead of 4. Let's try a math problem related to Boyle's law. A sample of oxygen with a volume of 500 milliliters at a pressure of 760 torr is to be compressed to a volume of 450 milliliters. What pressure is needed if temperature remains constant? So let's see what's happening here. The volume is going from 500 to 450, so the volume is going down. If volume goes down, pressure should be going up. You need to look at this relationship for every single problem so we can predict what our answer is going to be, so you can tell whether your answer makes sense. Volume's going down, pressure's going up. So you probably also want a formula. Here's my formula, P1V1 equals P2V2. P1V1 equals P2V2. So plugging my numbers into that formula, I end up with P1 times V1 equals P2 times V2. And I think I can do better with that L there. So when I'm solving that, I'm going to divide both sides by 450 milliliters. And notice the milliliters themselves will cancel out, so I'll be left with torrs. So 760 times 500 divided by 450 is going to equal to 844 torr. And that's Boyle's law. Next we've got Charles' law. Charles, well, it comes from Jacques Charles, who lived in the 1700s. He was a French chemist. And he said when temperature increases, volume will increase. So this is saying the molecules are moving faster. If the pressure is constant, the faster moving molecules, since they're trying to increase pressure on the container but they can't, they're going to make the container larger. Remember again the conversion between Celsius and Kelvin. Celsius is plus 273 is Kelvin. So first let's look at where the Kelvin temperature scale comes from. Let's say you had 0 degrees Celsius, which is right about here, and you were graphing temperature versus volume. So you would notice that for every individual gas, when temperature increases, volume increases, and these lines go up, and we have a positive slope. But they all don't seem to land in the same place. The thing is, if you take all of those lines and extrapolate them backwards until they hit that axis, so if we go on these lines back to here, it turns out that every single line for every single gas, totally different gases, all hit the axis at the exact same spot, which is negative 273 Celsius. That's where Kelvin came up with the idea of his Kelvin scale, because at 0 degrees, what he called Kelvin, is where every gas would have 0 volume. Now this temperature is not possible, it's only theoretically possible. It's called absolute zero, because it's not possible to have a gas that has no volume. If it has no volume, then it doesn't have mass and it's not matter. So absolute zero, which is 0 Kelvin, or negative 273 Celsius, is the coldest temperature possible. So we're going to be using Kelvin temperatures. Kelvin temperatures will never go negative, no matter what. The coldest possible theoretical temperature is 0. So you should never, ever, never have a negative Kelvin temperature. Let's work a problem. A sample of nitrogen has a volume of 300 milliliters at 20 degrees C. What temperature is required to change the volume to 250 milliliters? So the first thing you're going to do is change Celsius to Kelvin. Every single time, change Celsius to Kelvin. 20 plus 273 is 293 Kelvin. Every single time, change temperature to Kelvin. Then let's look at what's actually happening here. The volume from 300 down to 250 is going down, so temperature should go down. This is going to give us an idea of whether our answer is reasonable. And we need a formula. V1 over T1 is equal to V2 over T2. And let's just plug it in and see what happens. V1 over T1 is equal to V2 over T2. And in this case, we're going to cross multiply and divide, which means multiply the numbers that are across from each other and divide by what's left. So that's 293 times 250 divided by 300. And you end up with x is equal to 244.2 Kelvin. Here's the problem. Pretty much all of our thermometers are in Celsius, either Celsius or Fahrenheit, but I've never seen a thermometer in Kelvin itself. So they'll give you a temperature in Celsius, because that's what they read on the thermometer, and they'll want an answer in Celsius, because that's what you can read on a thermometer, but you have to convert it to Kelvin to work the problem, and then convert it to Kelvin when you're done. So convert it back to Celsius when you're done. So to convert it back to Celsius, we're going to subtract 273, which is left with negative 28.8 degrees Celsius. Notice that we said temperature was going to go down, and it started at 20 degrees Celsius and went down to negative 28 degrees Celsius. So all is well with the world. Our answer checks out. Next we have Gay-Lussac's law. Gay-Lussac's law says if temperature increases and volume is held constant, pressure will increase. This is why you shouldn't throw an aerosol can in a fire, because when the temperature increases from the molecules, that can is going to explode because the pressure will get too much. Let's work a problem. A steel cylinder contains a sample of neon at a pressure of 1 atmosphere and a temperature of 25 degrees C. What will be the pressure of the neon if the cylinder is heated to 800 degrees C, as you might have in a fire? So we're going to change everything to Kelvin, all temperatures to Kelvin all the time. Always do not use Celsius. This is 298 K and 1073 K. Now let's look at what's happening here. The temperature is going up from 298 to 1073, so the pressure should be going up. This is how we're going to check ourselves to see if the pressure goes up. You'll also need a formula. P1 over T1 equals P2 over T2. There's your formula. So let's just plug it in. P1 over T1 equals P2 over T2. Again, we're going to cross multiply. That is, multiply the numbers that are across from each other and divide by what's left. So that's 1 times 1073 divided by 298. And hopefully you get x is equal to 3.6 atmospheres, because the Kelvin's canceled out. And there's my final answer. Let's check it to make sure it's reasonable. We started with 1 atmosphere, we ended up with 3.6 atmosphere, and we said the pressure was going to go up. So everything looks fine to me. Let's combine these gas laws. So if we had P1 V1 equals P2 V2, and then we had V1 over T1 is V2 over T2, and we had P1 over T1 equals P2 over T2, we can combine all three of these things. So there's nothing held constant, no pressure, no temperature, no volume. Notice that pressure and volume are both on the top above temperature, and notice that pressure and volume can be multiplied together. So we can actually combine all three of these equations to end up with P1V1 over T1 equals P2V2 over T2. And there's our final combined gas law. I'm going to erase all this so I have room to work out my problem. Or at least as best as I can erase all this. So I have room to work it out. Alright, let's read the problem itself. A sample of argon, the gas in electric light bulbs, is at 760 torr, make that a better R, when the volume is 100 milliliters and the temperature is 35 degrees C. What must its temperature be in degrees C if the pressure becomes 720 torr and the volume becomes 200 milliliters? First things first, let's change the Celsius to Kelvin. So 35 plus 273 is going to be equal to 308 K. Then let's look at the relationship of the variables. Notice that pressure is going down, and if pressure goes down, the thing that we're looking for, temperature, should also go down. So according to pressure, temperature should decrease. But also volume is going up, and if volume goes up, temperature should go up. So according to volume, temperature should increase. This makes it a little bit harder to predict whether temperature, my final answer, is going to be higher or lower than my original. But notice that the volume is going up by half, doubling. So temperature should double according to volume. But pressure is not going down by half, it's not cutting in half, it's just getting smaller. So my general idea is that temperature should go up rather than down because the volume change is a greater proportion than the pressure change. So let's plug this into the problem. P1 times V1 over T1 is equal to P2 times V2 over T2, and then we're going to cross multiply and divide by what's left. So this is 308 times 720 times 200 divided by 760 divided by 100, and hopefully you're going to get x is equal to 583.6. As far as units are concerned, the torrs will cancel, the milliliters will cancel, and we'll be left with Kelvin. The problem is the question's asking for what's the temperature in degrees Celsius, not Kelvin. So we're going to subtract 273 from that answer to get my Celsius temperature, which is 310.6 degrees C. Now let's check the reasonableness of that answer. The Kelvin temperature, according to the volume, was supposed to have doubled, but notice that it didn't quite double from 308 to 583 because, according to the pressure, the Kelvin temperature was supposed to have gone down. So notice the temperature went up significantly, but not quite doubled because the pressure was kind of going against that trend. Okay, last one is Avogadro's law. Avogadro's law says if the moles of gas increases, then the volume will increase if pressure and temperature was constant. Essentially, it says if you blow up a balloon, the balloon will get bigger because you're putting more gas into it. So his actual statement was that equal volumes of gases, as long as they're at the same temperature and pressure, have the same number of molecules. So each of these balloons that we have down here have the same number of particles if they are at the same temperature and pressure, because the volume of the individual molecules is considered to be negligible. The gas molecules take up very little space on their own. So really the volume of the container is the volume of the particles. They all have the same number of particles. You could put this into a formula and do some math problems with Avogadro's law. It's not typically done, but it can totally exist, and that formula would be V1 over N1 equals V2 over N2. And then you could even plug that with it into the combined gas law that we had looked at earlier, P1 V1 over T1, to make it P1 V1 over N1 T1 equals P2 V2 over N2 T2. And what's even cooler is that you can use that combined gas law that has Avogadros and Boyles and Charles and Gay-Lussacs all in one to solve any one of the problems. So if you wanted to look, say, Boyle's law, you could just ignore the N1 T1 part. Or if you wanted to, say, do Charles' law, you could just ignore the P1 N1 part and only look at the V2 V1 T1 part. So you can kind of ignore or hide any part of the equation that you don't want and work with all the rest. Okay, these are the gas laws. We'll see you again next time for Daltons and Grahams.